Hello, you beautiful people. So today I want to show you the solution to your homework. There were two homeworks. So one was on the conversion temperature diagram, and the second one was on the reactor sizing. Okay, let's start with the first homework. So calculate the outlet mole fractions Xi for an adiabatic reactor with an inlet temperature of 250 degrees and a system pressure of 300 bars. What is the mass flow of ammonia leaving the reactor? And then some hints or assumptions. Assume chemical equilibrium at the reactor outlet. Use the conversion temperature diagram from the previous slide. There you can also find the inlet molar fractions. And assume a total mole flow at the inlet of n.0 total of 100 moles per second. Okay, let's have a look. So for 250 degrees Celsius, you just have to change the inlet temperature, and then by parallel shifting, you get this new enthalpy curve. And if you look here, then you can see, okay, at the outlet of your reactor, you would have a temperature of roughly, what is it, 490 degrees maybe, and a conversion of 42.5%. Okay, this can be seen here. And the first question was to calculate the mole fractions at the outlet. Okay, for this, in the last lecture, I gave you, the table here. Whoops. So basically what you have to do is first you have to calculate your inlet mole flows. This is not that complicated since you know the total mole flow n.0 is 100 moles per second, and from the diagram you can see the composition. So you have 21% of nitrogen at the inlet, so this means 21 moles per second of nitrogen. So for hydrogen it's 63%, this means 63 moles per second, and so on. And yeah, what you can do then is you know your conversion at the outlet of the reactor, since you can assume equilibrium. And this means by this equation, you can calculate your mole flow at the outlet. And if you know this, then you can calculate the molar flow, the mole fractions. Okay, let's do this. So we start from the table. We start with the mole flows at the inlet. This is just 100 times the percentage. It's very easy. And then you can do this. So let's go back. If we look here, so then you have to know your inlet mole flow minus minus your inlet mole flow of nitrogen times the conversion, or for hydrogen it would be 3 times the conversion times the nitrogen mole flow at the inlet. Okay, so this means 21. So for nitrogen, 21 minus the equilibrium conversion, 0.425 times 21. And if you calculate this, this is 12. For hydrogen, it's 63 minus 3 times the conversion times 21. And ammonia, you have no ammonia in the beginning, and then you get double the amount of the nitrogen consumed. So yeah, basically your mole flows are 12, 36, 17, and 16. And if you sum it all up, then you have a mole flow of 82.15 moles per second. Okay, and now you just have to calculate the mole fractions. So for this, you have to calculate your mole flow of nitrogen divided by the total mole flow at the outlet, and then you have 14.7%. For hydrogen, it's 44.10%, ammonia 21.73%, and so on. And in total, this should be 100%. Okay, so with this, you have the outlet composition of your reactor, which was one of the question. The other one was what's the mass flow of ammonia? So from this table, we know that we have a mole flow of 70.85 moles per second. If we know the molar weight of ammonia, 17 grams per mole, so you just have to multiply 70.85 by 17, then you get 303.45 grams per second. And in the homework, it was asked to have the mass flow in kilograms per hour, and this is 1092.42 kilograms per hour. So just this value here times 3.6, and then you go from grams per second to kilograms per hour. Okay, so that was homework number 1. The second homework was reactor sizing. And here you should do the same for a temperature of 250 degrees and a system pressure of 300 bars. You should calculate the reactor volume with the same assumption as before. We have a total mole flow of 100 moles per second. And the second question is if you want to achieve ammonia production of 3 tons per hour, what would be the total inlet mole flow and the reactor volume? Okay, how to do this? Yeah, you have to use your enthalpy curve again, and then you have to somehow get some points along the line. So maybe you could go here, and maybe there you can find, and somewhere in the middle you can easily get one, and maybe you can also assume the reaction rate in this point, and maybe this point, and so on. Maybe also this. Whoops, sorry. Wrong. Of course, I have to put it on the enthalpy line. Why can't I remove it? I see the rubber, but I cannot remove it. Okay, it should be there. Okay. And if you do this, then you will end up with a graph that should look like this. Your equilibrium is somewhere in the range of 42.5% is your equilibrium conversion. I draw this line, and again I just said, okay, the area that we have above here and here, this should somehow be close or be similar to this area. And if I want to do it, then I can calculate my reactor volume just by the inlet mole flow of nitrogen. So it's again 21 moles per second times this rectangle here. Okay, reactor volume is then 20 moles per second. The inverted reaction temperature is 22. That's what I found out. So it's if you wrote 25 or 20, this would also be fine. If you would write down 0.5 or 0.1, I would say no way. This is totally wrong. Okay. So, and then you will end up with a reactor volume of 7.07 cubic meters. So make sure that if you want to go from this value here to this, then you have to make sure that you take care of the moles, kilomoles, hours, seconds. So if you just take the numbers here, then you have to multiply it by 3.6, and then you get 7.07 cubic meters. Okay, second question was the reactor volume for 5 tons of ammonia. So by the molar weight, you can say, okay, 5 tons per hour should be equal to 82 moles per second. You have a conversion of nitrogen of 42.5%. And then you can use the table that we had in the beginning. You can use this to find the initial mole flow of nitrogen to the reactor. So this is 96.47 moles per second. And now you just have to change the mole flow. So from 21, you go to 96.47 moles per second, and then you end up with the reactor volume of 32.47 cubic meters. And if you want to know the total mole flow at the inlet, so then you know the mole flow of nitrogen. This should be mole, whoops. mole flow of nitrogen at the beginning, and you have to divide it by the mole fraction of nitrogen at the beginning. So this is 21%, and then you end up with a total mole flow at the inlet of 459.38 moles per second. Okay, thanks for watching. I hope you got the same results, or if not, then maybe you know the reason why. Hope this video helped you, and goodbye.